Second lecture this morning is David Burns, who's going to talk about congruences between derivatives of Artin L-functions.
So, is the microphone on? Microphone is on?
The red one.
It is on. Okay, thanks. So first of all, let me start by thanking the organizers for inviting me. I'm very happy to be here. What I want to talk about today is sort of a new observation about an old story. And so I will formulate a conjecture in the beginning of the lecture, and then I will describe a theorem, tell you something about the proof, and then at the end of the lecture, hopefully I'll have time to explain how it fits into a much wider picture, and what in the wider picture should also be true. So the old story is concerned with if you take a finite dimensional complex representation of the Galois group of a global field, it has an Artin L-function, and the famous conjecture of Stark is concerned with the leading non-zero coefficient of this L series. So the first non-zero coefficient an. So Stark has a very beautiful conjecture, and I'll just quickly recall that. If this is finite dimensional, factors through some finite extension, so it's a finite Galois extension, and I want chi to be a character of this group. If one fixes a finite set of places of k, non-empty, this is a global field, so it's non-empty, it's finite, and it should contain any Archimedean places if you're a number field, then in this context, this ring will be, or this group will be the unit group of the S integers elements of k which are integral outside of S. There's an abstract object which is just the kernel of a natural sum map from all the places of k over S, where you just sum the coefficients. And these objects by the Dirichlet regulator span isomorphic R vector spaces. In fact, they're equivariant with respect to the action of G, and the conjecture of Stark, the Stark conjecture, says the following, that if you take any phi, which is a homomorphism, G homomorphism from XS to OS cross, which is injective, if you take the leading term of the S truncated L function for the contragradient character chi, and you divide by a certain regulator, which is the determinant as it happens of, I guess, the chi component. I'll just say the chi component of phi of the regulator composed of the inverse of phi, loosely speaking. Stark's conjecture says that this leading term divided by this regulator, this determinant, should belong to the field of coefficients of chi. It should be an algebraic number. So this recipe is a rather explicit recipe, takes away the transcendence of the leading term. So this conjecture is interesting because if, for example, your L function vanishes to order 1, you can rephrase this conjecture in the spirit of a sort of a non-abelian version of Hilbert's 12th problem, in the sense that what happens is that in the order of vanishing 1 case, you can reinterpret this in terms of the existence of elements of OS cross, and you can show that the elements of OS cross which arise in this context actually generate the field that's cut out by the kernel of chi. So it's a non-abelian version of Hilbert's 12th problem, if you like. But what I'm really interested in today are the fact that in various cases, people have tried to do better. So in the abelian case, the refinements of Stark's conjecture, and these refinements were due originally to Stark, and then to Tate, Gross, Rubin, Christian, Popescu, and lots of others. And they have the effect of really bounding the denominator of this undetermined algebraic number. They tell you something about the denominator. They also tell you that as you let chi vary over different characters of this fixed Galois group G, so different chi factoring through a given Galois extension, that there are somehow congruences between these algebraic numbers. That's the nature of a typical refinement in the abelian case. If you take a non-abelian character, the refinements are very, very few and far between. So an analogous refinement in the non-abelian case would be interesting. As I say, if you take an order of vanishing 1, you're talking about Hilbert's 12th problem. And if you could say something about the denominator, or possibly even congruences in the non-abelian case, you'd be saying more things about these generators of the field cut out by the kernel of chi. But even in that case, there's very little known. There's only one really concrete case in which people postulated a conjecture. This was Stark raised the question and Chinberg formulated the conjecture, which was a refinement, weaker than the nature of these refinements, but his refinement was in a very special context. If your field K was Q, your character chi had degree 2, the L function vanished to order 1, and then a connection through the theorem of Deligne and Serre to modular forms allowed him to formulate a very concrete conjecture, really essentially about the denominator of this algebraic number. And that conjecture was basically proved for 9 examples computationally. So very, very little is known. So even if one is interested in computational mathematics, sort of formulating a refinement is interesting because if you're looking for algebraic numbers, it's extraordinarily helpful to know what their denominator is bounded by if you're using a computer. So there's some interest, both numerically and philosophically. So what I want to do today is to explain to you how, in fact, one can formulate, surprisingly, a completely clean universal refinement of Stark's conjecture, which doesn't distinguish between abelian and non-abelian, which upon appropriate specialization recovers all of the refinements I've listed, and which indicates all sorts of new phenomena, which surprisingly seems not to have been observed before. So that's what I want to talk about. And then at the end of the lecture, I'll explain what this universal approach actually, what it's motivated by and where it fits in a much bigger picture. Okay, so I first of all want to formulate a very concrete conjecture. That's 2, and then I'll talk about a theorem. Now, in order to keep the narrative flowing, I'm going to suppress some technical details. Nothing essential. Nothing that changes the shape of anything. But I'm also going to introduce a simplifying hypothesis, which is not necessary. It just makes things a bit cleaner. Okay, what's the hypothesis? I have a non-negative integer r, and the hypothesis, which I call hr, depending on r, is that this S is not an arbitrary set subject only to the restrictions that it's non-empty and finite and contains Archimedean places. I'm going to ask that S contains the Archimedean, all places that ramify, so that's only a finite set, but then somehow a distinguished set SR, and SR has 2 properties. Its cardinality is R, and if you take a place in SR, its decomposition group is trivial. So I'm introducing this hypothesis because I want to force the L function to vanish. I want to talk about derivatives rather than values. Having said that, of course, if R is 0, S is just simply containing the Archimedean and the ramified places. So I will also talk about values, but I want to generalize it. So example, sometimes this just means that it's containing the Archimedean and the ramified. If, two interesting cases, R is 0, when it obviously means this. And another situation would be, for example, if K was totally real, R was the degree of small k over Q, and SR was just the Archimedean places. If you are a totally real field, your Archimedean places split completely. They have trivial decomposition group. So this is not going to rule out lots of interesting examples. I'll explain at the end what happens when this hypothesis isn't satisfied. So I want to collect together the L functions. I want to bunch them up. I'm going to count them. According to those that factor through a given Galois extension. So I'm going to sum over all irreducible characters of this finite group G. I'm going to have the L function of the contragradient, and I'm going to look at a derivative. So I'm going to actually take away, I'm going to divide by z, which is the complex variable to the power r times the degree of chi. So this is changing as chi changes. And I'm going to run those together with the corresponding central idempotent of the character. So this is all sort of, it's a meromorphic CG valued function. This is the central idempotent for chi. So it's actually valued in the center of this algebra. So it depends upon R, so I'm going to call it R. It's an easy fact that HR implies this thing is holomorphic at z is 0. So what I want to do is I want to study the value of this function. If you like, it's close to being a weighted derivative. And I'm going to study its value at z is 0. Okay, so in fact, what I'll do is I'll define over here the central object that will run through the conjecture. So if I take a phi, just as Stark did, but with a slight twist, I'm going to run my phi the other way. Then I'm going to regard phi as fixed, and I'm going to define sort of a normalized version of the value of this function at z is 0. So I take the function, evaluate it at 0, but then I'm going to have an equivariant version of the regulator of Stark. So I'm just going to multiply by the reduced norm. I'm non-abelian in general, so the reduced norm is the determinant of the automorphism you get where you take the inverse of the regulator and you tensor with this. This is an automorphism of the real vector space spanned by xs. So it has a reduced norm. This is all an element, if you like, of the center. In fact, of CG, it's an element of the center of RG. I'm not insisting phi is injective. This need not be a unit, but it belongs to the center. So it's just a sort of a normalization of the value of this function at z is 0. Yes?
So even if phi were injected, you might be losing some leading terms.
Yes, indeed. I'm fixing the rth derivative in all components. Yeah. That's actually key.
Some L functions may vanish.
Some L functions may vanish, yeah. I mean, I may have more than R places splitting completely, and they all could vanish. But in fact, this is somehow key to formulating a natural integral statement. So it's very clean. The statement simply says that regarding phi as fixed, that remember this is non-abelian, so it's not going to talk about determinants. It's going to say that this normalized derivative is a ZG linear combination of elements which are themselves reduced norms you need more than one mi, where mi is an integral matrix. Now, this thing, one might imagine that one has taken away the transcendence by normalizing it in this way, but of course there are lots and lots of denominators in the game, for example from the idempotents. It's far from obvious that it's integral, but this is somehow the appropriate statement. In fact, in the sum hypotheses, one can even say more. So for the idea is that if you look at the characters of G and every irreducible symplectic character has the property that the leading term of the L function is positive, then one matrix will do. This is simply equal to the reduced norm of an integral matrix. But in general, you need more than one. So I'll just explain what this very clean statement has as consequences. So the first thing is actually, so it sort of obviously implies the relevant bits of Stark's conjecture. So Stark's conjecture for all chi such that the rth derivative, sorry, the r chi-1th derivative is non-zero. So that's not too difficult. In the context of the abelian refinements, if this is abelian, this is the determinant over QG of an integral matrix, so that's just an element of ZG. This is a ZG linear combination of elements of ZG. So if your G is abelian, it simply says that theta r belongs to ZG, and that's Rubin's conjecture. Actually, the very fact that there are denominators in the idempotents and there are somehow no denominators in the entries of the matrix, this is actually binding congruences, rather complicated integral congruences between the different components of theta r as chi varies. And one can try to make these congruences explicit, but it's rather difficult. But one thing I am suppressing is a very interesting aspect to the story, which is that one can actually predict that the columns of the matrix satisfy congruences. So in fact, there's a stronger version of conjecture 1 in which the columns of the matrices satisfy congruences which encode data about local reciprocity maps. Congruences which encode local reciprocity maps. Now, this stronger version, which I want to suppress today because I want to talk about a different aspect of the approach, the stronger conjecture 1 implies, when G is abelian, all of the conjectures of Gross and Tate and various other people, which were known as refined class number formulas. There are several in the literature, but there's the full version of this where the matrices Mi satisfy congruences with respect to their columns, implies all of these. I just want to suppress that today.
These congruences are formulated in terms of these augmentation type ideals in some ways?
Some are, yes, and then some are involved in directly with reciprocity maps. So,
what was the stronger conjecture 1?
It is a conjecture in which one postulates the existence of matrices Mi the columns of which satisfy certain mutual congruence relations. But as I say, I would rather like to suppress that today for lack of time. I just want to say somehow it's a universal framework. If one can understand why conjecture 1 should be true, then one has understood really why all of the refinements of Stark's conjecture that have been studied in the literature, why they should be true. I should also mention that there's a recent conjecture of Dasgupta in which he formulates, technically speaking, an explicit formula for the gross Stark unit, and that's also a consequence of this conjecture when the stronger version when you specialize to G abelian. What I'm wanting to say is that this is the non-abelian generalization of the conjectures you will find in the literature. Now, this motivated by Christian's talk yesterday, I wanted to sort of specialize today on a different aspect, which is this does tell me something, obviously, about the denominators of theta r. It's the reduced norm of a matrix with integer coefficients. Now, in some cases, one does know what the denominators of theta r are actually like. And so I just wanted to recall. So if G is abelian, so theta 0 is actually really just the value of theta 0 at 0. The regulator, the reduced norm, can be ignored in that case. And the Deligne and Ribot say that this has no denominators. Now, one of the technical things I'm omitting is that, in fact, one has to slightly normalize this with an auxiliary set of places. But again, that isn't central to the story. I won't ignore that. However, if you take a general group, for example, if you take certain anticyclotomic extensions of Q, so G is a dihedral group, what you can show is that this has denominator p to the n. So effectively the group order. So in the non-abelian case, things are very different. The abelian case, this is a beautiful observation which is key to the formulation of Brumer's conjecture that Christian mentioned yesterday. In the non-abelian theory, nothing like that can work in a straightforward way. The natural analog has denominators.
Even if you adjust it with this additional.
Even if you adjust it, yeah.
Basis.
So one has to do something about this, and I'm just going to tell you a rather neat way of describing the denominators. So if I take the rational algebra and decompose it into its simple components, so one has the order that is underlying everything is ZG. But if you choose a maximal order that contains ZG, then for any integer d, there's a corresponding decomposition of the matrices over the maximal order. Where the mi is m intersect ai, if you like. And so for any h, I'm just going to define this to have components hi. So I'm going to introduce an ideal which accounts for the denominators of the functions that I'm interested in. So definition. This is completely algebraic. I'm going to take elements of the center of the maximal order with the property that if you take any integral matrix, then y times the sum. So if I sum over every component where hi is invertible, So I'm only summing over the components where this component of H is an invertible matrix. So sum over those components, take the inverse and multiply by the reduced norm. And then the requirement on Y is that this should be integral. So the first observation is that if G is abelian, this is just what you want it to be. And if, in general, there's a result of Jacobinsky, which tells you that for any, let's say, rational character chi, this is the idempotent. So if chi is rational valued, multiplied by the order of G divided by the degree of the character belongs to delta G. And in fact, this looks a very cheap lower bound. The example of the this example shows it actually can be sharp. So this is can be a sharp lower bound. And then the easy fact, which is what I wanted to say, is that if I take anything in this denominator ideal and any matrix which has integer coefficients, if I take the reduced norm of the matrix and multiply by the element of the denominator ideal, I'm integral. So this construction was first, as far as I'm aware, I read it first in a paper of Andreas Nickel. But it's a very neat algebraic construction, which in this context nicely incorporates the fact that the denominators behave very differently. Okay, as I said, the observation of Deligne and Ribot was really fundamental to the formulation of Brumer's conjecture, which asserted, as Christian mentioned yesterday, that this element of ZG annihilates the ideal class group when it acts. So having gotten rid of the denominators of reduced norms of integral matrices, conjecture 1 tells me that theta r is an integral linear combination of such elements. So if I take theta r, it's at least reasonable to ask. So conjecture 1 tells me that theta r for any d in the denominator ideal, d times theta r has no denominators. It's in ZG. Conjecture 1 tells me it's a ZG linear combination of things like that, and the easy fact tells me that d kills the denominator of anything like that. So it acts on the ideal class group, and one can ask, what's the chance it actually annihilates the ideal class group? That turns out to be a little bit optimistic, but what seems to be true is that it annihilates the ideal class group when you throw away the distinguished set of places SR. And even that's not quite true. You need an additional factor x, which is 1, or g minus 1. It's 1 if r is 0, or SR are the Archimedean places. So these are the cases I talked about at the beginning, where hypothesis HR was automatic. Either you had no places to speak of, or the places were all Archimedean, a totally real case. And in this case, I'm not in that, so G is anything in the decomposition group of a non-Archimedean place. So that is the conjecture, and I just wanted to, again, very straightforward, very simple-minded, give you a few examples of what this conjecture says. So if I take K to be a number field, G to be abelian. If G is abelian, then the denominator ideal is ZG, so my D could be 1. So I'll take D to be 1. I'll take the R to be 0. So the distinguished set of places which are splitting completely is just the empty set. So H0 is automatic. If R is 0, I can take X to be 1. And SR is empty, so S infinity union SR is just S infinity. OK, S infinity union SR is just the ideal class group. So this conjecture 2 implies that theta 0, which as I observed before is just the value at 0 of the L function, belongs to the annihilator over ZG of this. SR is empty, this is just the ideal class group. So that's Brumer's conjecture. So that the statement at least recovers Brumer's conjecture, but it does much more besides, because you can now look at it in lots of different contexts. For example, K is totally real. And I take my parameter R to be the degree of the bottom field. I take my distinguished set to be the Archimedean places, which, as I observed before, split completely. Then this just tells me that X d theta R, which is, remember, theta R in this case is a weighted, theta SR was the sum over the R chi 1 derivatives. So it's the value at 0 of a very high derivative, then normalized by a suitable regulator. This just belongs to the ideal class, annihilates the ideal class group. So here G isn't abelian. This is a very high derivative. And so what conjecture 2 encapsulates is really a version of Brumer's conjecture with no restriction on the group being abelian or on the nature of the order of vanishing of the L function. So it's very clean. And in this context, that seems to be essentially new, the idea of such a clean statement. The only other work in this kind of direction I'm aware of is due to Victor. And he used induction techniques to try to get annihilators from abelian, to try to sort of build up Brumer's conjecture into a non-abelian statement. Whereas this one does everything very directly, very cleanly. Actually, maybe I just give you one other example, just to give you a flavor of what it also contains in between these two extreme cases. The third example, let's take K to be Q, Q to be the real field, epsilon m is 1 minus e to the 2 pi I over m, 1 minus e to the minus 2 pi I over m. So this is real, so I'm going to have one place splitting completely, which will be the Archimedean place. And if you unwind the definition of theta r in this case, what you find is that if you take any homomorphism from the units to ZG, if you evaluate this homomorphism on epsilon m may not be a unit, but it is a unit if I multiply by 1 minus g, and then it says that this annihilates the class group. So this statement is the main annihilation result proved by Rubin in a paper in Invenciones in 87. So it's sort of the universal, again you see the g minus 1 here coming from x. So one gets a very nice, clean philosophical approach, which basically encapsulates everything in the literature. And so what can one prove? So the first observation I made is that it implies cases of Stark's conjecture. So if one is going to prove anything, one is going to prove cases of Stark's conjecture, which rather limits unconditional results that one can prove, of course. So the best one can hope for is that these conjectures 1 and 2 should be true whenever Stark's conjecture is true, known to be true, and that's basically the case. So I'll just list some cases, and then at the end of I'm going to finish the lecture by telling you how this theorem is proved and how it links to other things. If, for example, so K is abelian over the rationals or an imaginary quadratic field, standard cases. But this is much finer than Stark's conjecture. The standard cases are not easy to prove, but they are true. K is a function field. With mild technical restrictions at the moment. Another interesting class of cases, there's an infinite family. Of K over Q with a Galois group, the quaternion group of order 8. So that's an interesting case because the one symplectic character for this family, it has root number -1, which in the context of conjecture 1 says that you need more than one matrix. But it's true in this case, quaternion of order 8. I just want to, I'm going to give you some corollaries of this theorem, which are, rather than simply restating the consequences I elucidated, it's also possible to prove weaker versions of these conjectures under rather more general hypotheses. And so I'm just going to tell you some of the things that come out from this machine.
I'm sorry, I don't understand the third statement. I mean, the conjecture concerns a pair, let's say, K over Q. And you say it's true if there exists an infinite family. What does that mean?
Oh, beg your pardon. So it's true if, for example, you're right, it belongs to a certain infinite family.
And what you just said about the epsilon factor, it's not automatically true even if you have this quaternion Galois group. It takes some local behavior. No?
It is. But what I'm saying here is that for this family, the root number is -1.
So that's an assumption. That's part of the hypothesis.
No, if I describe the family for you, that's a consequence of the description. One can prove it for this family. And what that means is that in conjecture 1, it really is the case that one needs more than one term in the sum. So that's kind of an interesting family, because conjecture 1 is true, but you need more than one matrix. Okay, so let's just unwind the standard case. If I have an abelian extension, then I have for all phi and for all g, that g minus 1 times the I guess real abelian, sorry. The weighted derivative of this, the weighted derivative is just the determinant over Rg of the regulator with a -1 composed with the function phi that you've picked. This guy, so you take, in fact, since all characters are abelian, this is just the k to q derivative of the L function in each character. You evaluate that at 0. You normalize it by this choice of regulator. This annihilates. This belongs to the annihilator of the class group. So it's extremely explicit. It's just a very general recipe for producing annihilators of class groups from things which in principle are very transcendental. This is non-zero, I should say. These cases are non-zero. If you specialize to k equal q, so you're looking at first derivatives, then this gives a new proof of Rubin's theorem. That I mentioned before. So
this would be sort of a base change of Rubin's theorem?
yes, it sort of lets, in that context, there is Rubin's theorem, and then this is a theorem that lets k vary. So as k varies, of course, the derivative gets higher.
I understand.
Yeah. So what about totally real fields and non-abelian extensions? What can one actually prove? So here is k is totally real, and I take my chi. Let's say it's rational valued. So one can prove something unconditional. Then the statement is that for all phi, and all g, in the union over the decomposition groups for any non-Archimedean place. And so here you've got the weighted derivative. You multiply by a certain reduced norm. And then, unfortunately, because it's slightly weaker, you have to multiply by some factors. But again, these are Artin L-functions. I'm not saying G is abelian. G is non-abelian here. This is a very high derivative of the Artin L-function. You evaluate it at 0. You normalize it by this reduced norm where phi has been chosen carefully. And then there's a slight fudge factor here. This annihilates the class group. So it is integral, acts on, and annihilates the class group. So again, a very explicit statement about annihilation of arithmetic objects in highly non-abelian situations. There's a remark here. If one attempts to try to remove the condition that chi be rational valued, one can do it conjecturally. There's the so-called p-adic Stark conjecture at s equal 1. That's due to Serre. And one can remove the hypothesis in corollary 2 that the character is rational valued. So that's an interesting remark simply because the p-adic Stark conjecture at s equal 1 is actually a slight refinement of Leopold's conjecture. For various characters, this is equivalent to Leopold's conjecture. If you have a permutation character, this is the same as Leopold's conjecture for that character. And what it means is that this is a modulo this conjecture, a generalization of recent work of Boyuk-Perduk. So he has a nice paper recently where he assumes Leopold's conjecture and he constructs annihilators of class groups in a situation where G is a cyclic actually. And he constructs an annihilator for the p part for p not dividing the group order. He assumes Leopold. This is a slight refinement of Leopold, and you get a very natural non-abelian extension of it.
P-adic gross at s equals 0 would not suffice here, I suppose.
I don't know, I must say. offhand. But so this p-adic-Stark conjecture actually naturally comes up if you try to make descent in Iwasawa theory, which what I'll talk about at the end of the lecture. Now there's one other really nice case. So I carried around a phi, and one has to be. So this phi differs from Stark's. I mean, in a silly way, Stark ran phi the other way. And somehow, what's key to making an integral statement is to look at phi in the other direction. But having said that, there's no canonical choice. Okay? But in one context, there is a canonical choice of phi, which is that if you have function fields. If you are in a global function field, then the degree map gives you a canonical phi. So if I choose a canonical phi, what happens to this? So let's consider K now a function field. And let's change variable. I'm going to let t be the characteristic of k to the power minus z, where z was the complex variable before. So I'm going to define a zeta function of t, so that it's this theta function I had before of z, I guess. I think I mean that. I've changed variable from z to t, so the leading term of this is now not going to be transcendental anymore. Leading term at t equals 1 rather than z equals 0. So the degree map gives the canonical phi. And if you plug this phi into the formula, what do you get? So you get a rather neat theorem, which is this. So if I take this function, it's a meromorphic function of the complex variable t, and I take any integer r, for any r, such that the rth derivative of this function is holomorphic. At t equal 1. One has. So if one takes the rth derivative, evaluates at t equal 1, and then slightly normalizes it, this annihilates the class group. Or the S class group. So here, phi hasn't disappeared, it's been chosen carefully. And if you use this choice of phi together with the change of variable, you get an extraordinarily explicit statement. So this is derivatives directly annihilating class groups. Wherever this derivative is holomorphic at t equal 1, its value annihilates the class group, modulo this fudge factor. So very explicit. So the formalism is somehow quite convincing, but why should we ever believe it? And so this is how I'll end the lecture. I'm going to tell you how you prove these theorems and how it links into a much more general picture. But independently of the general picture, these are just simply concrete and unconditional statements. The proof of theorem 1. Theorem 1 said the conjectures 1 and true were true in an array of cases. So the key point conjecture 1 and 2, conjectures 1 and 2 actually follow implied by sort of equivariant refinements of so depending on whether you're in the number field or function field case, if you're in the number field case, this is simply it follows from a refinement of the Bloch-Carter conjecture. So the Tamagawa number conjecture of Bloch and Carter. And if you're in the global function field, one doesn't have a Bloch-Carter conjecture, but the relevant conjecture is due to Lichtenbaum, and it's a leading term conjecture. For zeta functions. It's a leading term conjecture in terms of Weil et al. Cohomology. That's the one that's the one that works very nicely. So somehow the point is that one deduces this from a very big conjectural formalism, and that formalism happens to be true in certain cases. So the cases that I listed in Theorem 1 are situations where the equivariant refinement of these conjectures are actually known to be true. So the point of Theorem 1 is that it lists cases in which these refinements are actually proved.
The ET and C in function fields would not be defined from
Yes, yeah. This is, I'm sort of, the original conjectures, of course, Bloch-Carter's Tamagawa number conjecture, the equivariant refinement I'm referring to is the ET&C. The ET&C over function fields really is the equivariant refinement of this that I'm referring to.
so you don't need the refinement, you would need just Lichtenbaum.
No, you need a refinement of Lichtenbaum, but I think it's fair to write Lichtenbaum here.
Right.
Yeah. So the cases in Theorem 1 are cases in which these conjectures are known. More general conjectures are true, have been proved. So somehow the real reason why you should believe conjectures 1 and 2 is the fact that they come from, a very large formalism of conjectures, which is very convincing. In fact, because they come from the Tamagawa number conjecture, it's also true that they are a consequence of the main conjectures in non-commutative Iwasawa theory that you would have heard much about earlier on. So the issues of descent that have been referred to from main conjectures to rather concrete, complex conjectures of this kind, this was dealt with in a paper that I wrote with Ottmar Venyukov. So descent can work in this context, and it shows that these conjectures are consequences of main conjectures in non-commutative Iwasawa theory, which is how this links in with other talks that may have been given. So given that it comes, in fact, to prove that it follows from these conjectures is rather elaborate. It's sort of, these conjectures are phrased in terms of virtual objects and relative algebraic K-theory, and it's sort of the computations in homological algebra and K-theory are required to convert between that beautiful but rather inexplicit formalism to these statements which are extraordinarily explicit. So it's rather elaborate, the argument, which I chose not to describe, but I simply want to end by saying that, now clearly the point is, if it comes from a large, very general framework, this framework applies in many, many different contexts. So what does one get in other contexts? Well, in the general context of a Tamagawa number conjecture for an arbitrary motive over a number field, the explicit statement, it does depend upon certain aspects which are particular to the case that I'm dealing with in this lecture, but slightly weaker versions of the conjectures can be phrased totally generally. So you have a version of the conjecture for elliptic curves, for example, where the role of phi for an elliptic curve is played actually by simply an integral valued height pairing. So the normalization, if here is the leading term, or the suitable derivative of the Hasse-Weil L function, then it's normalized by dividing by the discriminant, if you will, or the height coming from an integral valued height pairing. So a suitable normalization will have minimal coefficients. It will annihilate the Tate-Shafarevich group. It will satisfy mutual congruences between their different components. And these are all consequences of the main conjecture of non-commutative Iwasawa theory that one can actually see at least on a computer. So, and that's it's a very general framework, is what I'm trying to say, which surprisingly also includes in it some extraordinarily explicit statements like this one, which don't seem to have been observed before. But I think I've run out of things to say.
So, you said at the beginning you were going to make some remarks about this hypothesis that you put in.
What happens when it?
That it,
Yeah.
the sense in which it isn't necessary.
Yeah, it isn't necessary. So here's an example where it's not used. This was just the nth derivative in every component. Whereas when I used this r in this context, this r actually remembers the degree of the character. You know, so for character chi, the derivative you look at is r times the degree of the character. Whereas here, I'm just looking at the nth derivative. So hypothesis HR is not satisfied here in any context, which is why you pick up this. That's not best possible, but it works. So in the context that I mentioned at the beginning, where you have a character, let's say, coming from modular forms, you have a degree 2 character which is odd, so the order of vanishing is 1. That doesn't satisfy hypothesis HR for any r, unless your character, well, in fact, it's degree 2, it doesn't satisfy it for any r. So the conjecture in that case will pick up some very explicit additional factor. But with HR, when you have a somehow very rigid structure, the conjecture gets better. That's the idea.
Actually, so here's a question. So in the behavior of determinant or congruences, where characters pop up, if you and the Taylor-Oliver logarithm situation, if you have a character whose character values are all already congruent to 0 mod a big power of p, you actually get some extra congruences. I mean, that is, you should get easier integrality. I mean, at least if you're going prime by prime.
So in formulating conjectures 1 and 2, they're very general, which means that in some cases they're best possible, like the anticyclotomic extension. It's actually a best possible prediction. But in many other cases, it's not best possible because somehow the structure of the group means that you might be able to get away with smaller denominators. Mm-hmm. I also glossed over today the congruences that should be satisfied by the columns of the matrices. But that's sort of a whole interesting kind of family of congruences. And so in the literature, there are constructions, I think originally by Gross, about algebraic height pairings coming from local reciprocity maps. So this is, you have an integral matrix and its columns satisfy congruences which are the exact non-abelian generalization of that. So such congruences also have consequences for the denominators. I must say at this stage I don't know what they are, but they do. So there are all sorts of really explicit statements in the non-abelian theory which somehow I think they weren't spotted before because everybody had phi going the wrong way. Sort of convenient to run it this way.
Except for Rubin, maybe.
So Rubin's conjecture, you're right. He has phi going into ZG. Yeah.
So regarding this stronger conjecture that you didn't quite describe explicitly, the one that incorporates the congruences for the columns of the matrices. If you restrict that to the abelian case, do you think you would capture this conjecture of Darmon that Rubin and Maser just proved over Q?
So I think for a technical reason, probably not. I always thought of that as like a base change. And the difficulty with base change here is that to get the integrality, you've sort of fixed a derivative in every degree. And it might be true in some degrees that derivative happens to have value 0. And so the base change statement can, in this context, still be dividing 0 by 0. So I don't know about that one. But
So to me, that's like a Rubin-Stark conjecture, but before applying the phi. You're saying something about congruence is satisfied by this Rubin-Stark element before applying your phis.
I would have to think about that. But I should say there's obviously an Iwasawa theoretic version of this, where you choose norm-compatible or compatible families of phi, and a compatible this thing, and so you have an Iwasawa theoretic analog as well.
What's your theorem 2?
Mhm.
After all, it's a purely algebraic statement on
Mhm.
the Jacobian of a curve.
Mm-hmm.
Can you see it that way? I mean, or even the derivative of z here, acting on the Jacobian, it's like something very complicated.
Yeah, no, it's, so I first of all thought this must be obvious.
Right?
I first of all thought it must be obvious, since it was such a clean statement. But if one analyzes some examples, it doesn't seem to be obvious. You know, if you see how the nature of the derivative changes, then, you know, it's interesting in and of itself to say that this accounts for all of the denominators. You know, this statement says it doesn't have any denominators, but more than that, it annihilates the natural arithmetic object. And I must say, I don't see I haven't tried to prove this theorem somehow freeing myself from the general philosophy. So I see it from a particular direction at the moment, but it must be true for another reason, I guess.
But even for r equal to, I guess the first r is just 0, right?
Mhm.
For r equal to 0, can
Well,
you see it on the curve? It's Jacobian.
Well, for r equals 0, actually it becomes simply a weaker version. R equals 0, this is the order of g squared. This is just the value of the zeta function at t equal 1. It's a weak version of the Brumer's conjecture, which was...
That's not my question. My question
Sure.
is someone, yeah.
Well, that's proved by Deligne, using the methods that Christian referred to yesterday of one motives. That's actually, you know, this is, it's slightly weaker. If you specialize to r equals 0, you get a weak version. But that weak version has a geometric proof.
One last question,
Yeah.
because it's an organizer. Dispensation.
Well, it's a simple manipulation, but the point is, you have a general theory in which the structure of G does not play any role. And on the other side, you told us, look, this is sharp, because in the case of dihedral, you have this denominator. My question is it thinkable that you have a theory in which the structure of G tells you and makes all the assertions then sharp in some sense?
It may be. So the best that I have at the moment, of course, is this ideal of denominators, which is a very nice construction. But it's very sharp in the anticyclotomic case. One can compute. It's the denominator is best possible in that case. In other cases, it's a little bit wasteful, actually.
Yes,
If you take a quaternion extension, Q8, the quaternion family I had, in that case one knows that the value of the L function for the symplectic character is non-zero. So one can compute it. One can actually compute everything in these cases, and it's wasteful. What this says is that the class group is killed by, I think in that context, it's killed by something like 16. I mean, you know, philosophically speaking, whereas one can actually verify that the class group has order 32, I think, but exponent 2.
So this is what I'm saying.
Yes, no, it's a good question.
There must be a feature of the group which...
There are features of a group which at the moment I cannot see. But it is true that in some cases this is sharp.
Okay. If there are no more questions, let's thank the speaker again.